Hi everyone, welcome back for yet another session of Good Morning Science, the home edition. My name is Dr. Alon Eisenstein and I'm with Pueblo Science. Got my trusted t-shirt, Pueblo Science. We are a charity based in Toronto in Canada, and just for those of you who are joining us for the very first time, I'm just going to give you a very little tiny introduction of who we are and what we do and why we do the things that we do. So, in a really short form, Pueblo Science is a charity that was founded 10 years ago by two Filipino scientists, Dr. Mayor Salvanor and Dr. Cynthia Go, and our mission is to improve the quality of science education in rural communities, in developing countries, in the Philippines, and everywhere else in the world. And we've been doing that for 10 years, and we're looking forward for another glorious 10 years to come. Now, because we do professional development for science teachers in these communities, we keep on coming up with ideas of how to engage kids in fun ways with really easy to find materials at home. And that's why we're going to do this exercise today and a few experiments that we've tried over the past 2 weeks. You can find them on our social media outlets. And for those of you who are new for this, you can always subscribe to our Facebook page or our social media outlets, and also click on the donate button somewhere up there to help support our charitable mission if you believe that what we're doing is important and you want to support our work. But if you just want to do this for the fun of it and want to keep in touch and see what we're coming up with, do follow us, like us, share us, and keep your ears open for next things coming up. Okay, now let's see what we're going to do today. So today we're going to do 3 experiments. Here's the materials that we're going to need for today. We're going to need a mason jar. We're going to need some water. We're going to need, I've got a screen mesh here, or just some tights or socks. I've got chocolate bar. I've got a ruler. I've got some colorful markers and paper and scissors. And a glue stick, and the only thing that's missing from the list is a microwave oven, but that's in my kitchen upstairs, so we'll have to do that later when we go up to the kitchen. So hang in there. Let me clear up this mess on the side where I'm going to start working, and then we'll start with the very first activity. So if you haven't got a chance to get the materials ready, now you can pause or watch it later and get all the materials ready, and then we can get started. So hang in there, we're just about to begin. Welcome back. Let's get started with the very first experiment. For this one, it's actually quite simple. We don't need many materials with us. We just need a piece of paper. It could be colorful or white, it doesn't matter. We need some glue, so I'm using a glue stick, but you could use white craft glue or even tape, and scissors. Okay, so what are we doing? What we're going to do today is we're going to make some strips or loops. So to make a loop, I'm just going to fold the paper into half, and I'm going to cut it along the center. Now, I do have scissors, but this is quicker for me. If you know how to tear your paper straight line like this, go for it. Otherwise, you can just use your pair of scissors. Either way, it is fine. So I'm gonna cut it into 4 strips, and they will be roughly of equal width. And we're gonna play some games with these strips and see what we can come up with. Okay, so here's what we're ending up with. So this is a nice activity that relies on a bit of geometry. So geometry as a field of science, a field of mathematics, tells us how we define shapes and the relationship between parts of the shapes. And so for this one, we're talking about different geometric shapes. So this nice strip of paper is now, from a geometric point of view, a simple object that has 2 surfaces on each side. There's 2 surfaces. Now, the reason I know that it has 2 surfaces is because there's an edge separating these 2 surfaces. So there's one edge that goes all the way around, and separating that one big long edge, which is a continuous edge, is separating the two surfaces. So when we have one edge separating two surfaces, here's what it looks like. So I'm going to use two colors just to make it a bit more vivid and see where we end up with, okay? So I'm going to color it. Now this is a bit of arts and crafts mangled in the science activity, so some people like to, instead of using science, refer to these activities as STEM to indicate science, technology, engineering, and math. But if you get artistic and use your expressions of your perception of how you see things with colors and shapes or voices or any other way, we can add the arts into the STEM, making it STEAM. So whether you like STEM or STEAM or science, it's all good as long as we know what we're talking about and what we're trying to do. So now I have one surface which is red, and to get to the other side of the surface I need to flip it on its belly, and I'm going to use blue just to color code my second surface. And now what we see is that now we have two surfaces and they're separated by a single continuous edge. Now if I'm going to take my glue stick and I'm going to put some glue on this side, there we go, and I'm going to fold it and glue it into a band or a loop. Now we have a band, and what you can see is that this band has, again, two surfaces. Even though I folded it, it still has two surfaces. However, this time there are two edges. So there's one edge on this side, and I can flip it to the other side, and there's an edge on the other side. And the way it works is that if I want to go from one surface to the other surface, I have to cross an edge. That's how we separate the edge from the surface. And you can see that if I'm using my black marker, I'm going to tilt it slightly like so. If I'm placing my marker and I'm walking along inside the surface and I'm going all the way around, I end up meeting back exactly where I started. Here, I'll point it to the camera. You can see that I created a continuous strip of line of black ink that meets at the beginning. And as long as I'm within the surface, I don't need to cross any edge. If I want to color paint over the black, I have to start from the red, but then I have to physically cross over an edge like here or the other side in order for me to cross from the red to the blue, right? So basically what it means is that, again, even though I folded it, I still have two surfaces separated by the edge. Let's put that away. Now let's try this again. Now this time around, I'm going to color code again. I'm going to color code the red on one side. If you want to be more adventurous, you might want to look at a different color, but I'm mindful for the time and I don't want you to keep waiting and watching me color code. Oops, look at that. I wasn't paying attention and I coded both sides with the same color, where in fact what I meant to do is color code one side with red and the other one with blue again, just so we can differentiate the two sides of the surface. So now I have two sides. Again, same as before, I have the red side on one side and the blue side on the other side. And once again, we have to cross an edge to go from blue to red and vice versa. But this time around, I'm going to put some glue here. But now what I want you to do is, instead of folding it in exactly the same way back into a loop, we're going to add a twist. So, and I do mean that literally. I'm going to twist my paper like so, right? So I'm taking my strip of paper and I'm twisting it. And only after I twisted it am I going to fold it so the blue and the blue, where's the camera? Blue and blue are meeting together. They're touching one another. And now I have another loop. It looks slightly different. It looks twisted, right? You see, this one is twisted. But what's happening right now? If I look at my red, if I look at my red color and I walk along the red, at some point the red turns into blue, and then the blue turns back into red. That's weird. So the red and the blue surfaces meet each other without crossing an edge. What does that mean? Well, let's try this again. In this case, I'm going to do it from the top. Ready? Okay, so I'm putting my marker over the red, and I'm going to walk over, and I'm going to trace, and I 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 trace, and oops, I need to go the other way around, and keep going, keep going, keep going, keep going, keep going. And I never had to lift my pen. Well, I did because I was going from left to right, but I didn't have to lift my pen to meet the origin of my black line there. So what does that tell me? It tells me that since I've never left the surface and I never had to cross an edge, then by definition, I'm still on the same surface, which means that this loop, it has only one surface. Isn't that weird? We started with a double surface loop, exactly the same strip of paper. We just twisted it before gluing it, and now we have a loop that is twisted and it has a single surface. And this is called a Mobius loop, or a Mobius strip, or a Mobius surface. And what's cool about it is the fact that, unlike a regular loop, it only has one surface and one edge. So if I actually were tracing with my finger over the edge, I would always come back to where I started. I can't paint it. You won't see the marker if I trace over the edge, but if you do that with your finger, you'll get back to exactly where you started. Again, indicating that this surface has one surface and one edge, unlike the regular loop that has two surfaces and two edges. Isn't that neat? Now here's where it comes even weirder. I'm going to take my scissors and I'm going to cut. Here, let me put this here. I'm going to make a cut halfway through the middle, and then I'm going to cut my loop, my band, my ring along the center line. And what happened? Well, not surprisingly, if I started with two surfaces with two edges and I cut along the center, creating a second edge here and a second edge here, now I end up with two identical bands, which means a total of four surfaces, two here and two here, two edges here and two edges here. So four surfaces, four edges. What happens if we cut the Mobius band? If we start with two surfaces and two edges and we cut it into half, doubling it to four surfaces and four bands, if we start with one surface and one edge, can we make two, making it two surfaces and two edges? Let's see what happens. So I'm going to cut this with my scissors again, all the way along the center line, and see what we end up with. And look at that. I ended up with still only a single loop, a single band, only this time I have two twists instead of just one, and I still have just one surface and one edge. So that's an interesting property of a Mobius band, that every time you cut it, instead of going from one twist, you end up with two twists, and three and four and so forth. So if you want to play with this at home, keep at it and try different colors and see what you can come up with. And also try, instead of making one twist before you glue it, what happens if you twist it twice? Now this time it's going to be hard for me because the strip of paper is too wide. But if you cut it uh, uh, thin enough, it should be easy enough to twist it twice and maybe three times, and then see what happens when you do that. So I hope you enjoyed that little activity. So that was a Mobius band. Isn't that cool? Surface, edges, a bit of geometry. Cool. Let's go to the next activity. Okay, I'm going to clean up and get back to you with the next activity that has a bit of water. I like water. Okay, let's move on to the next activity. So in this activity, I'm going to use, I hope the mirror is not in the way. So in this activity, we're going to need a mason jar, a glass jar. Now you could actually use just a drinking glass, or if you have a very solid, very stiff plastic cup, that works well as well. And here's what we're going to do. So this activity requires water, and I'm going to make a bit of a mess here, so you'll have to forgive me. So I'm just going to stand up so you won't be able to see my face, and I'm going to do this activity just as I am over a big bucket to keep it from making a big splash all over. But this is essentially this is the idea of what we're trying to do. Okay, so here's what we're gonna do. So in this activity, I'm taking my jar of water and I'm pouring a bit of water, and I'm going to put my palm of hand over this. Now, if you don't have a large enough palm to cover the entire mouth of the cup, either look for a smaller mouth, a cup with smaller mouth, or you can also use cardstock or playing cards. Ideally, something that's plastic, so you can cover it. So you can just put a little bit of plastic card over it. But we're just gonna use the palm of my hand for this one. So if I put my palm of hand over it and the palm of my hand there, and I turn it upside down, you can see the water in the jar, right? What's going to happen if I let go of my hand? Well, gravity, as we know it, likes to pull things down, so obviously it's going to spill and empty out altogether. But if you happen to have a mesh, a screen from the window, you can put it over the mouth of the jar. And the reason I like to use mason jars is because it has this nice sealing ring, so I can just screw the sealing ring into place, and then I have my screen mesh over it. Now you can actually do this as a magic trick if you want. If you hold it sideways and people can't see the screen, you can tell them that you can defy gravity. We like to call this an anti-gravity, defying gravity trick. So you can see that I can pour water in through the mesh, right? So I'm pouring water inside my jar. There we go. Now, if I put the palm of my hand over the jar and I flip it upside down, then obviously you can see how I'm holding the water inside, of course. Now, if I'm going to count to 3, and you can expect that the water is going to fall down through gravity, right? But if you say magic word abracadabra, you do it very, very carefully, you can still see the water suspended here inside the jar. Now, remember that we didn't put anything other than mesh, and you saw the water could go through the mesh going in. But if we flip it upside down and it's perfectly horizontal and we let go very, very, very gently, going straight down instead of sliding or shaking it, the surface tension of the water holding the water film onto the screen is strong enough to keep the water from falling through the tiny holes of the mesh. Now, if you want to make the effect more significant, because it is a magic trick, right? You can tell people that, hey, did you see the invisible cap? No, because there's no cap. If I shake it, it actually drips. If I shake it again, it drips again. I can shake it more, and there it goes all the way out. Isn't that cool? Now, if you don't have a screen mesh like me or a mason jar, if this was a regular cup, you could just take an old nylon socks or tights or stockings, and you can see that if you actually pull on it, you can see that it's very nice and meshy. So you can put it over the mouth of the jar like so, and then you can use a rubber band to hold it in place. So this works perfectly well as well. Unfortunately, you'll probably lose the magic trick effect because you can't actually, oops, and it actually doesn't go in very well. But you can fill it with water. Because you can see it dangling, you can't hide it as well as if you're hiding a screen mesh around the ring. But the idea is exactly the same. You flip it and then you let go, and you can see how the mesh that is a lot of tiny holes allows the water to go in if you apply force. But if you flip it upside down and let it sit for a split second horizontally, the balancing of the forces horizontally makes the thin film of water so strong that it keeps the water from going down to gravity. But again, shaking it will let everything fall down, agitating that thin film that is due to surface tension of the water. There we go, right? So that was our anti-gravity trick. This is probably one of my favorite. I've done it with kids outside, and they loved getting soaked when they spill the water. Okay, I hope you liked that one. And now let me just clean up and dry up this mess and get ready for experiment number 3, which will be upstairs. Okay, so hang in there. Okay, welcome back. I dried up all this big mess I made with water. So for the last experiment number 3, we're gonna use a chocolate bar and a ruler and a microwave oven. Now I don't have a microwave oven here, so let me take you upstairs to my kitchen and let's meet up at my kitchen and try this experiment, and then come down again and I'll explain what we're doing. I'll just give you a hint. We're going to measure something very, very fast. We're going to measure the speed of something that moves really, really fast. Ready? Okay, let's go. Oh, sorry, I forgot the computer. Here, let's go. Sorry, there we go. Okay, here's the door, and let's go to the kitchen. Okay, welcome to my kitchen. And for our third experiment, here's what we're going to need. We're going to need a microwave. There we go. We're going to need a chocolate bar. Now, this chocolate bar needs to be at least 10 centimeters long. Just plain chocolate. I'm using dark chocolate, but it really doesn't matter. But it should be one long bar. Now, if you don't happen to have access to a really long chocolate bar, that's not going to matter too much, because I'm going to show you a trick how to make it not so important this time around, okay? And other than the chocolate bar and the microwave, we're going to need plates. I'm going to use a big plate and a small plate and a ruler. There we go. If you happen to have a handy, you can also bring a grater. I'll show you in a second why. Okay, so what are we going to do? We're going to attempt the impossible. We're going to attempt to measure the speed of light. Yeah, you heard it right. We're going to try and see how fast does light move. And we're going to use a little trick that we know that light is a source or a form of electromagnetic radiation. And what do you know? The microwave oven is an oven that uses electromagnetic radiation to heat your food. And so if we use this electromagnetic radiation from the microwave, we can then use a little bit of math and a little bit of physics and a lot of chocolate to figure out how fast is the speed of light, and then see how close are we to what is considered to be the official value of the speed of light. Okay, how's it gonna work? So the first step is that the microwave that we're going to use, we're going to need a microwave that has a rotating plate. So if you don't happen to have a microwave oven at home, unfortunately you can't do this with us today. And if you happen to have a microwave oven and it doesn't have a rotating plate, that's not going to work either, because the microwave radiation will be moving too much inside the oven. So what we really need is this type of microwave oven that has a spinning plate, and we're actually gonna take it out. We don't need it, or the nice little rotating ring. And the reason being is that once we remove these rotating plate and ring from the microwave oven, the radiation that is generated from behind here, the plastic, the cardboard cover, is actually a standing wave, which means that the radiation is not moving anywhere. It creates a specific pattern of hot spots and not so hot spots. And that's why if you ever warm up your food in a microwave oven, you always notice that sometimes some parts of the food are warmer than others, and you always have to stir it up to make it even, right? So that's why, because the microwave oven's radiation creates hot spots. It doesn't create a uniform hot temperature like a regular oven does. And we're going to use that trick of hotspots to figure out the speed of light. So what you're going to do is, because I have the little knob that turns the spinning plate visible, I'm going to take a small plate and I'm just going to cover it like so it doesn't disturb my plate. And then we're going to take our piece of chocolate, unwrap it, and then put it laying flat on the plate and put it right in. And then we're gonna turn on the microwave oven for about let's see, we're gonna turn it on maximum power for about 15-20 seconds or so. So let's see what happens. Okay, now as it's warming up, what's going to happen is the microwave radiation will create hot spots, and only those spots will start melting before everything else. And so if we get this right, we're going to be able to then use that and use some physics to measure the speed of light. So that was 20 seconds. Let's take it out and see what it looks like. Now, the problem with this experiment is that sometimes it's hard to see where the melted parts are. And you can see some places are a bit shinier than others. And sometimes it's harder to get it right. And if you turn it upside down, you see, oh, this is melting here. And there's another spot here. Sometimes it's at the edges, right? So you can see how I missed it a bit, and there's an edge melting here. So it's going to be hard to measure. So I'm going to show you a different trick, and that's going to help solve the problem of also having a bar that might not be long enough. So the way to go around and solve the problem is I'm going to take a fresh new plate. And this time around, I took one of my chocolate bars. Yeah, I bought a few, of course. I can't just buy one. And I grated them just using a regular food grater. You grate them. I'm not going to do it on front of the camera because it does make a lot of mess. But the good thing about it is that once it's grated, we can then take a spoonful, and you don't really need that much. One spoonful is really all that you need. And I'm going to scatter it around the plate like so. And that will give me a really nice even coverage, and hopefully will make it a lot easier to see where the melted hot spots are in the chocolate. Incidentally, you actually can do the same thing. Instead of using chocolate, you can actually use the same idea using butter. You just need to cut really thin pieces of butter and place them around the plate like so. So let's see what this looks like right now. So I'm going to put my shaving of chocolate in the microwave oven, and I'm going to turn it on maximum again for 20 seconds. We're going to watch the clock. and then see how that works, okay? So in about 10 seconds, we'll see if the shaving works better than just a full bar of it. Okay, 3, 2, 1. That's enough. Okay, now here's the fun part. Now, again, it might be hard to see in the camera, but you can see that there are darker areas and not so dark areas here. And so it's actually a lot easier to see where the melted spots are. You can see a dark patch here and a dark patch. So there are actually 3 spots. So we're going to measure the distance between the 2 close spots, one to the other, roughly from the center. And you can see that it's roughly about 6 centimeters apart. I think the angle is a bit hard to see, but if I measure from the center of one circle to the other, it's about 6 centimeters. Now, if this is hard to you to see where the melted spots are, here's another trick you can use to make this activity slightly more visible. I'm going to just tip it over into my box of shaving, and I'm going to reuse this, okay? And voila! You see how easy this is, right? So now, this is why if you actually melt shavings instead of the full bar, you'll see the nice circles, and then it's a lot easier to then take a ruler and measure from center to center, and you're going to see about 6 or 6.5 centimeters in between them. And so that's going to give us one number. That number is, we're going to use about 6.2, 6 centimeters and 20 millimeters. So 6.2 centimeters, that's the distance between the 2 spots of melted chocolate. The physics of electromagnetic radiation will tell us that if we know the distance between 2 hot spots, to get the speed, we also need the frequency of the radiation. And conveniently enough, in most microwave ovens, you can actually find the frequency here in the back. So I'm going to turn it around. Let's see if we can find it. Look for the number where it says frequency in usually units of megahertz or gigahertz. So here's what we're going to see. I don't know if you can see close enough. Can you see it here? It's 2,450 megahertz. That's the frequency of the electromagnetic radiation. And now that we know the distance, right, 6.2 centimeters between the 2 hotspots, and we know the frequency of the radiation, which is 2,450 megahertz. The next step is going back to the drawing board and doing a bit of math on the paper and see what we get for the speed of light. Okay, so hang on tight. We're going to go back to the table and use our math skills to calculate the speed of light and see how good we come close to it. Okay, hold tight. Okay, we're back from the kitchen. Let's put our heads together and try to use some knowledge with physics, electromagnetic radiation, what that really means, and at the same time a bit of math. And we're going to put all this together and see how we can use this simple experiment with chocolate in a microwave and actually calculate the speed of light, which is so fast it's mind-boggling. Okay, so let's see what we need to know. First, electromagnetic radiation, and then we can do the calculation. Okay, so let's talk a bit about electromagnetic radiation and what it really means. So, what does electromagnetic radiation mean? It means that we're generating an electric field, which means it's like little tiny magnets, and they're moving around up and down, up and down. And so if I draw some direction from left to right, or right to left, then the strength of the magnet, the little charges, the strength goes one direction, so we can imagine this is the plus side. So it becomes more and more and more positive, and then it subsides. But then it goes further and further down to become more and more negative, and then it goes back up again. and then it goes up and down like so. So when we look at an electromagnetic wave, we see that at certain time of the wave, it has a strong positive um, uh, wave or tide or hill, and at other times it has a very strong negative field, right? So you can imagine as if this is a strong positive magnet and this is the reverse polarity, so this is the minus. Now the thing about this is that you see that it oscillates up and down, positive and negative, and goes back to positive, and it does that at constant intervals. And so if we measure from the peak of the plus to the next peak of the plus, the distance in space between the two places where we have the two peaks of the plus is called lambda, or the wave length, like so. We can do exactly the same if we measure from the absolute lowest minus to the next absolute minus, and that is exactly the same wavelength. Any point, arbitrary point, if we go to the exact same place along the wave, it will be the same wavelength. So that's constant. And so the relationship between the wavelength and the frequency, which is how long it takes. So wavelength is in physical space, it's centimeters and meters. If we measure the time it took the wave to go from here to here, and we count how many times these oscillations repeat per time, per second, that's called frequency. And so the speed of electromagnetic radiation is calculated by the frequency, S, multiplied by the wavelength. So if we know what the frequency of the wave is, and we know the wavelength of that electromagnetic radiation, then the product of these two numbers should give us the speed of light. That's what we're looking for. Now, if you remember, when we actually did the experiment in the kitchen, we saw that the frequency of the microwave was listed behind as 2,450 megahertz, which is essentially 2,450,000,000 hertz, like so, right? So the frequency is just simply a number we plug in because it's listed on the microwave, 2,450,000,000 hertz. That's the repetition of the oscillation of the electromagnetic wave. Now, if you remember, I told you that in the microwave we have hotspots. How do these hotspots relate to the oscillation of the strong positive field and the strong negative field? Well, the answer is both the positive and the negative fields produce energy. And so the maximum energy is found both in the exactly where the maximum positive field is, but it's also found where exactly the maximum negative field is. And that goes again to here as well. So positive, negative. And what you can see is now the length we measured on the chocolate was exactly the length between two adjacent hotspots. Therefore, the wavelength is twice, right? So it's twice the distance of two hotspots. And so, since our hotspots were 6.2 centimeters apart, if we multiply that by 2, we get 12.4, right? So then lambda is now 12.4 centimeters, or in meters, that would be 0.124 meters. If we put all this together, what we end up with is that I'll do this way. The speed of light equals 2,450,000,000 hertz multiplied by 0.124 meters, which ends up as 303,800,000 meters per second. That's the value we ended up with. Now, you might be asking, well, how close is it to the official speed of light? Well, the answer is the official speed of light measured with very sophisticated, very accurate instruments is in fact approximately 299,800,000 meters per second. That's approximation, not accurate to the absolute accuracy we have today. So if this is roughly the number, you see that we got 303 million and the actual number should be just under 300 million, which means that we are just about 1%. So we're roughly, or about 2%, I guess. We're about 2% off, 1 or 2% off, which, if you consider the fact that we did this experiment only once with a microwave and a chocolate bar, that's actually not too bad. I'm actually surprised it turned out so close to the actual value. But that's part of the fun of it. A simple experiment at home with your chocolate bar and microwave, and you can get, within a pretty decent accuracy, the speed of light. Okay, so we're done. We've got 3 experiments. We've folded strips of paper to make bands that, when you cut them, you end up with 2 identical ones, or if you add a twist, you create a Mobius loop, and when you cut it down the center, you get another Mobius loop, but you don't multiply it. What you end up with is multiplying the twists. So that was a bit fun of geometry. We then played with a mason jar, and we put some water in there, and because we covered it with a mesh, whether it's your nylon stocking or your screen from the window, those tiny holes actually hold the water so tight with the surface tension of the water that if you do it carefully and invert the jar, even if it's full of water, the surface tension creates a film so strong it actually defies gravity and holds the water in, even though gravity is pulling on it so strong. And finally, we did some yummy physics and math, getting some chocolate into the bloodstream. Using chocolate to measure the speed of light. I know what I'm gonna do now. I'm gonna unwrap this little chocolate bar and see if it tastes as good as it looks inside. And I would like to invite you again to join us next week for another edition of Good Morning Science, the Home Edition. As I started off, I would like to thank you for choosing to spend the time with me, and I hope that you love what we do at Pueblo Science. If you want to see future episodes, please subscribe to our YouTube channel, our Facebook page, or follow us on Instagram and Twitter. And if you believe that what we do is important and you would like to support and show your support in our work, please do click that donate button in the feed on the Facebook page, or just go to our website. There's a donate option there as well. But regardless, I hope that you all stay safe, stay at home, and don't forget to use the opportunity to do lots and lots and lots of science at home. This is me saying goodbye. Have a great day. Stay safe. Stay healthy. Bye.